we talked a little bit about differentiability, and we identified places where functions are not differentiable, right? To differentiate is the verb for to take a derivative. Right? If we differentiate a function, it means we're taking the derivative of that function. We're going to do that a lot better and more easily starting today. I'm going to start to give you guys we're going to start to develop the shortcuts for taking derivatives. So not having to do the whole limit thing. So close up the Chromebooks and have a look. So we said, where are functions not differentiable? Well, any place where limits don't exist, you can't take a derivative, right? Derivatives depend on limits. And so the most typical would be discontinuities, right? If a function is discontinuous, it's not differentiable. We remember we made the statement on Wednesday that differentiability implies continuity, right? So for something to be differentiable, it implies that it is continuous. It has to be. But functions could be continuous and still not be differentiable. Hence, example 2, corners, right? If there's a corner on a function, and we looked at an absolute value function, right? It has a V shape to it. Well, you at the apex of the absolute value function, at the point of the V, you can't, I used to call it vertex, you can't define a derivative there. Because if an ant takes a step to the left as compared to a step to the right, he's going to experience different slopes, and so there is no tangent line, right? And that's really what a derivative does, is it gives us a slope of a tangent line. So at corners, we don't have derivatives. Even though the function's continuous, it's not differentiable. And then we looked at one more example, which was a vertical tangent. And the example we looked at, as I recall, was that, right? We looked at x to the 1/3, and we said, yes, indeed, if we look at x equals 0, the tangent line is infinite. And so you can't, the derivative stands for the slope of the tangent line. If the tangent line has no slope because it's vertical, you can't have a derivative, right? So here was the example we looked at for an absolute value function. That's a corner, right? We could do another one. I just invented a piecewise function that has a corner, right? At 0, if the behavior of the function is negative 4x to the left of 0, and x squared when x is, that's supposed to be greater than or equal to, let's change that. Greater than or equal to 0. Then when the ant steps on that point right there, he's gonna transition from some large negative slope, negative 4, instantly to a slope of a tangent line that's horizontal, right? And you can't do that. You can't make an instantaneous transition like that. That's a sharp corner, right? So that would be no derivative there. Here's an example of a discontinuity, right? So at all of the integers on the step function, the greatest integer function, you've got these jumps, and so at those places we can't define a derivative. The function's discontinuous. Here we can't define a derivative at 0, right? Because there's a gap in the function, okay? Okay, there's another type though, that not all books even deal with this. The Math Excel for School does. I don't even think our regular textbook does, but let's talk about it because it's a word that'll come up. A cusp. So a cusp is just a subset of the set of vertical tangents. It's a type of vertical tangent. But a cusp is when, it's like if you combine a corner with a vertical tangent, essentially is what it is. It's an infinitely sharp corner. Okay, so the derivatives from the left and the right approach opposite infinities, right? So let's look at what that might look like. So if we took the function f of x equals x to the 2/3, for example, that's a cusp. If an ant is at the point 0, 0, which is defined, right? I can plug 0 into this, and I just get 0 back. If the ant took a little tiny ant step to the right to get a sense of what the tangent is, he would get a tangent of positive infinity, right? And then that's gradually gonna decrease to lesser positive values. You see that? Because he walks away from it. If the ant walks backwards to the left, that ant is going to see a slope of negative infinity. How do we distinguish that from positive infinity? Because if he continues his cute little ant steps to the left, he's going to get values that are increasingly less negative, right? You're going to get shallower. Does that make sense? So it's just that trend. Everybody see that? If we take these two tangent trends together, they come together at infinity, but this one's negative infinity and that one's positive infinity. And the result is we get this really ultra sharp corner. If I zoom in on something like this, what I'll see is that those curves just come together and it looks really vertical, right? Kind of get, I don't need to be more, I mean, you get the idea. We don't need to beat a dead horse here, but that's what a cusp is, okay? Infinitely sharp corner. So you get infinite slopes, but opposite directions. So it's infinitely sharp. Okay,
Wait,
I'll go back. Yeah,
no, can you just go to the blue one? Like where all the things are written out?
that one?
No, the things are written out, like all the
Oh,
things, you know?
right there.
Yeah,
Sure.
yeah.
You want me in that picture?
You're not in it.
Okay, so graphs of derivatives. So let's look at this now. This is, so you guys, who's in physics? Okay, so we're going to talk a lot of physics here in the near future. You've talked about kinematics, right?
Yes.
Okay. Well, we're going to take that to the whole new level here. I mean, real soon. So graphs of derivatives, you'll see why soon. Graphs of derivatives, the skill I want you to develop is to be able to recognize, if I give you a function, what the graph of the derivative would look like, and if I give you a derivative, to recognize what a possible version of the original graph could be. Okay? So let's try this. I'm going to graph a function in blue. This will be f. I want you to tell me what the graph, don't say it out loud, I want you to think about what's the graph of the derivative function going to look like. Okay? Before we do that, let's remind ourselves, what's the relationship between a function and its derivative? It might seem a little counterintuitive now, but it won't soon. You're really used to this. What does a derivative do again?
It's the slope of the function.
Slope of a function. So we did some examples. Like I think one example we did the other day was we said if f of x equals x squared, we calculated the derivative function, f prime of x, to be 2x, right? It was pretty amazing. What that function allowed us to do was to take any value of x we wanted to, plug it in, and it gives us the slope of the tangent line at that point, the slope of the curve at that point. Right? Remember that? So if we take f of, let's take 2 for example. Let's take something different. Let's take 3. So f of 3 equals 9, correct? So that's telling us that the point 3, 9 is a point on the graph. Everybody agree? Okay. F prime of 3 is what?
6.
Okay, what's that telling us? Okay, good. It's telling us that the slope of the tangent line at that point is equal to 6. Amazing, right? So that's what a derivative function does. It tells us the slope of the curve for a given value of x. So let me ask that question again then. What's the relationship between the graph of a function and the graph of its derivative? Okay. Well, if the derivative is telling us the slope of the tangent line, the value of the derivative equals the slope of the curve, f. What is the slope of this graph anywhere? 0. So for example, if I pick that point right there, it's going to translate to a derivative whose value is 0. If I pick that point right there, it's going to translate to a point whose derivative is 0. In fact, they all do, right? So would you agree that f prime just looks like that? Yes, sir.
Are derivatives always when
No, not at all. With
so
some,
we take the derivative of the derivative?
you can't. It's called a second derivative. We'll get there. Yeah. Okay. And there are higher order derivatives than that. Oops. So I just want to do more of this. Okay, so let's keep playing this game. I'm going to give you more of these. So how about, here's the original function. think what the derivative's gonna look like. You don't need to have exact numbers, just sketches would fine. So what do you think? Liz, what can you tell me about the slope of that function? It's going up, so what's the slope? Positive, does it change? Positive and constant. So how would you graph a function that's positive and constant? Would you agree? Okay. Does that make sense? So no matter where, now our ants, we kind of got cut off at the end on Wednesday, but I was telling you about these highly evolved calculus ants that have the slope sensors. So as they're walking along this blue function here, their slope sensors read a constant value, right? That's positive. So whatever their slope sensors read, that should be the value of the derivative function. Let me say it again, the value of a derivative equals the slope of the function, right? Okay, another one.
I know this one.
What is it?
You want me to draw?
Yeah, you can draw it.
Okay. Well, I kind of know what it will look like.
Go for it.
It's gonna be, I don't exactly know where, but it's gonna go negative and then 0 and then positive.
Good.
What?
Okay,
Yeah.
that's right.
I don't know where it goes on the thing.
Okay, so that's the right shape. Now let's put it in the right place, right? So now think how she got that. What Katie's doing here, she's saying that if you think, what's the ant doing here? His slope sensor is large and negative, right? So if we draw a little tangent, it's large and negative, so we're going to get a value of the derivative that's large and negative. Down here, the derivative is negative, but less negative. It's a smaller negative number. Agreed? So that's gonna move down to a point that's somewhat less negative. Okay, where is probably the most important point here in getting this graph correct?
Yeah, the minimum of the curve is going to be 0.
Okay, so right there, would everybody agree that's the place where the tangent line is horizontal? What's the slope of any horizontal line? 0, right? So that's going to be the place. Does that make sense, Katie, how now we know why that goes through there?
Yeah.
Because that's the horizontal part of the tangent. And then it's symmetrical, isn't it, right? This is just presumably a parabola. So it's symmetrical, so over on the right, it's just going to gradually, the slope is increasing at a steady rate, and so we're going to continue our trend, and it's just going to look like that. Okay, make sense? Now let me ask you this. Would I have had a different answer if I had started with this green parabola instead?
Nope.
No. That's pretty profound. You see that? The green parabola, assuming that those parabolas are, neither one of them is stretched. They're just regular old parabolas, but all they've done is they've been offset vertically. You see that offsetting the parabola vertically had no impact on the derivative? Because all the derivative cares about is the slope of the curve. It doesn't really care where it is, right? So the tangent lines, if I line them up vertically, like this tangent lines up with that one, those tangents would have the same slope, wouldn't they? That's all we care about, is the slope, right? So that's an important point that we'll come back to many times, that there are multiple values of a function that can give you the same derivative, and those multiple values just consist of offsetting it vertically. Okay? Offsetting it vertically does not change the derivative. Okay. Another one. How about okay, that's a good place to start. So right there, let's just say that's the place where it's got a horizontal tangent. So that's going to be the place where the derivative has a value of 0. Ah, okay, parabola. How come? Explain.
Because when you're going to negative infinity, the
slope is gonna be positive infinity.
Okay, right? So those are large positive values, lesser positive values, lesser positive values, right? So the value of the derivative function is going from large positive, less positive, 0. Other side is going to be the opposite. Small positive, bigger positive, bigger positive. That looks like a parabola, doesn't it?
Why is it, I'm so confused, why is that?
Because if I draw a tangent there, isn't that a large positive slope?
I think what's coming from 11, it's coming from like below like the ground, and as it goes up, it's like,
This is the same
it's
slope.
going up, the slope, yeah.
The slope is flattening out, right? It's flattening out as we go up. Here, I'll give you an example. Let me give you a visual on this one. What do you know? I just happened to build a little thing here that'll help us out with this. What are the odds? What are the odds? So if we look at something like this, okay? So here's the function f of x equals x cubed. Okay, I'm going to calculate a derivative. The derivative function is just g of x, right? And I'm just going to drag a. A is the value we're inputting into the function, okay? So as I drag a along, you can see that red tangent line. When I'm clear down there, what would you tell me about that tangent? Steep and positive. In fact, if you look down here at the slope, right now the slope is positive 6.75. If I drag this to the right, the slope is decreasing, but it's still positive, right? Decreasing but still positive, decreasing but still positive, 0, right there. Well, I can't quite get it up. Right there, 0, right? And now it's increasing but positive. Well, if I just add a curve that matches the values of the derivative, that's it, right there. Okay? Look at that point right there. That point on the curve, this is the derivative function. Notice the value, the y value of the function as I drag a. So when a is 1.3, the value of the function we don't really care about. The value of the function is, who cares? If I put a label on it, it's 2.197, but who cares? The value of the derivative of the function is 5.07, right? Well, there, I'm plotting those values on the green graph. Everybody see that? So as I drag a backwards, look what's happening. As the derivative decreases, the green function goes to 0, but when I pass through 0 to the left, it just gets positive again. See? Does that help?
Yeah, I was thinking, okay, why I was so confused was because I was thinking of it in terms of like a negative and positive infinity and not the slope.
Oh, I got you. Yeah, all it is the slope, right? And that's really easy to do. It's easy to make that, to get confused on that. What about, let's do a sine function. Oops. Yep. Okay, so here's our sine function, right? Now look at the outputs for the derivative. So I should get a 0 derivative where? Right there, right? If I can get it to that spot where it's flat, that's pretty close. I'm getting really small values, and if I was a little more skilled here, which I'm not, I would get that right to 0. Okay? So that's a place where the derivative function should have a value of 0. Agreed? So there's where the derivative should be right there. The green's going to be the derivative function again. Where's the other place where it's going to be 0? The next place. Right there, where the tangent's horizontal. Right? If I drag this function up to there, it should be 0 again. Where is it going to be at its maximum? Ah, interesting. Right? Where is the derivative going to be a maximum? Derivative of the blue function? Of a sine curve? What do you think? Yeah. Halfway in between the peaks, right, the extrema, peaks and the valleys of the sine curve, that's going to be where the curve is the steepest. And so right at 0 ought to be the place where the value's the largest. And what do you think the slope's going to be there? It's going to be 1. So what do you suppose the derivative of a sine function is? It's a cosine function. How about that? Okay. Right? Oops, what am I doing? I never know. There we go. Okay. So let's try one more of these. I'm going to give you a real tough one here. Oh, it's doing this again. Why is it? There we go. All right, so why does it keep doing this? My computer is really wigging out today. Keeps getting real slow. Okay. Again, you guys tell me. I'm going to draw a picture. Maybe. Come on. It's not going to work, is it?
Let's just use the whiteboard.
Everything you use is
It just breaks. Yeah.